Okay, as we all filter in, I'd like to introduce our next talk. This is Lauren Christofko from Baylor University, and she's here to talk to us about why age matters.
All right, thank you for the introduction, and thank you for all of you to wake up this morning and come to see my talk. I'll be talking about my dissertation work that looked at the relationship between zebrafish developmental stage and sensitivity to diphenhydramine. So as we're all aware, over the past decade, there have been a variety of changes in terms of chemical management, with the addition and modification of various legislations in the North American and European regions, specifically in the North American regions with amendments to TSCA, and in the European region with the addition of ECHA legislation. And this is encompassing not just thousands of chemicals, but actually tens of thousands of chemicals. The TSCA inventory having 85,000 compounds in its inventory, and the ECHA database having almost 17,000. And one of the hurdles that has come up as we're trying to proactively identify compounds is how do we generate all the toxicity data to accompany these lists? With traditional testing methods being time-intensive, resource-intensive, and of interest here, organism-intensive. And so one of the hurdles has been how do we generate this data but not necessarily sacrifice or continue with animal welfare but not necessarily sacrifice any of the breadth and depth of knowledge that we might get from this, from these studies. And the recommendation has been to move towards alternative testing strategies. The one that I will focus on today is the fish embryo toxicity test, or FET test. As most of you are familiar, this encompasses alternative life stages, embryonic and larval life stages of zebrafish. And it's looked upon favorably for a number of reasons, including the fact that it encompasses developmental stages or organogenesis, is fairly rapid and higher throughput, and it's easy to make observations of the transparent embryos. And as this has been recommended as an alternative to traditional testing methodologies, a variety of publications have looked at the sensitivity of the FET model in relationship to some other tests such as the FET embryo-larval test. And generally, we've seen high correlation in the sensitivity between these two models. But I did want to point out that there are a couple of studies that have identified that different developmental stages may be more sensitive than others. In some cases, embryos being more sensitive than larvae, and vice versa, with larvae being more sensitive than embryos. And so my dissertation wanted to get into this question to better understand if there's a sensitivity shift across developmental stages surrounding the FET test. But before I was able to do that, I had to identify a class of contaminant to study. I ended up studying antihistamines for a number of reasons, one of which was that previous work in our lab had identified that antihistamines have an increased relative hazard to other pharmaceutical classes. Antihistamines are also a commonly used pharmaceutical. If you suffer from allergies, you've likely already taken an antihistamine. And there's a wealth of pharmaceutical data or mammalian toxicology data in existence for this class of contaminants. And so I had done a hazard assessment of antihistamines, identifying a number of gaps, in addition to the fact that we are relatively data poor for antihistamines. And so I identified diphenhydramine as a model antihistamine for study. And then I wanted to evaluate, as I mentioned, the toxicity of the FET model for traditional endpoints such as mortality, as well as alternative endpoints such as behavior across a suite of developmental stages. And ultimately, at the end of my talk, I'll start to dive into why we might be seeing some of these developmental shifts in sensitivity. And so what you'll see here on the bottom left will be the LC50 values for the 3 developmental stages that I studied, 0 to 3, 3 to 6, and 7 to 10 days post-fertilization. On the bottom right will be a corresponding dose-response curve for each of these stages. And then for those of you who haven't stared down a microscope at as many of these as I have, I'll also add photos of representative of each developmental stage just to give you a little bit of bearing. And what you'll notice as I superimpose each developmental stage is a fairly distinct leftward shift in the dose response curve, corresponding to an order of magnitude decrease in the LC50 value, with the oldest stage, the 7 to 10 days post-fertilization larvae, being the most sensitive of these developmental stages tested. I published this in 2015 in the Association of American Pharmaceutical Scientists journal, and this led me to wonder if this age-dependent sensitivity would not only be evident for traditional endpoints, but also for alternative endpoints. So I opted to look at zebrafish behavior with the viewpoint system, which you can see on the bottom left there. It's a system that makes use of a camera and tracks behavior via locomotor responses. And the protocol that I developed, you can see an example of on the bottom right there. It's a 50-minute in duration protocol that alters light and dark photo periods, where you can see there's a 10-minute dark acclimation period followed by 2 cycles of 10 minutes light, 10 minutes dark. And similarly to the mortality data, I'll superimpose each developmental stage. But to give you your bearings again, on the x-axis we have diphenhydramine concentration. On the left y-axis we have distance traveled. That's represented by the black and white bars for the dark and light photo periods. On the right axis we have zebrafish survival, represented by the line graph, and then the last item, the vertical dashed line, is the therapeutic hazard value, or the calculated aqueous concentration that we would expect to result in internal concentration equivalent to a human therapeutic dose. And what you'll notice again, as I add each developmental stage, is we see another distinct shift in the sensitivity of the organisms, with the 7 to 10 days post-fertilization organisms again being the most sensitive and being the only developmental stage that had altered behavior at levels below the calculated therapeutic hazard value. This was published last year in Aquatic Toxicology, and after identifying this shift in sensitivity for both traditional and alternative endpoints, I really wanted to get a better understanding of why am I seeing this shift in sensitivity. So I went back to a central tenet in toxicology, that the dose makes the poison. So I wanted to see if there was a shift in the internal concentration that these organisms were receiving across these developmental stages. So on the x-axis will be time in hours, and on the y-axis will be diphenhydramine concentration. The vertical dashed line in this instance is corresponding to the natural hatching period of these organisms. So you'll note in the photo that these organisms are coronated or in an acellular membrane. And from the first hour post-exposure up through that natural hatching period, we see a fairly consistent internal diphenhydramine concentration that significantly increases after hatching. So I was curious if the chorion was influencing internal concentration of diphenhydramine. So I conducted the same exact experiment, but I enzymatically dechlorinated the embryos before dosing. And interestingly, I saw a very similar internal concentration trend for diphenhydramine, where for the most part, within the first 48 hours, we really see a very consistent internal concentration that again significantly increases after that natural hatching period. When I contrast that with the developmental stage, the 7 to 10 days post-fertilization organisms, which I previously identified as being the most sensitive, we see a completely different uptake curve for diphenhydramine, where within that first 24 to 48 hours, we see a much higher extent of uptake. Matching this with 1 week further in development, for 14 to 18 days post-fertilization organisms, we again see this higher internal concentration reached sooner. And both of these larval uptake curves really similarly mimic an uptake of diphenhydramine that we've experienced for adult fathead minnows in our lab. And so in conclusion, I was able to identify an age-dependent sensitivity of zebrafish to diphenhydramine, and this seems to be correlated with internal dose of diphenhydramine. Fortunately or unfortunately, I graduated, so I didn't get to go further and see what the driver was for the difference in uptake. That could be I have a number of hypotheses if that might be to either gill development, which starts to take place during this time, or if there are other dispositional changes that are happening. However, future work would be needed to better understand what is driving the uptake differences that I've seen here, and if that extends to other contaminants, especially as we are pushing to go towards alternative models to meet some of the data gaps that have been identified for some of the regulatory frameworks. So I thank you all for your attention, and I'll take any questions. Yes?
I'll just looks like you have the data present. Did you convert your internal doses to lethal body burdens in terms of millimoles per kilogram, or something that you could think of in more toxicological terms?
That's actually a great point. I hadn't done that, but that's worthwhile to consider. This last chapter is under review. It's been accepted with revision, but I think we could probably calculate that and add that in. That's a great point.
It might be interesting in the sense to normalize it to other compounds for, that might be in that class of studies.
Yeah, no. Thank you for that comment. Thank you.
So I was curious, you mentioned that the most sensitive time point of development was 7 to 10 days. The organisms are growing, obviously, and their ability to metabolize is becoming greater. Mm-hmm. So that's one thought I had. The other thought is feeding. These embryos during that it's the euthyral embryo stage, so they're freely feeding, and if that food isn't present right in front of their noses, a lot of times they'll emaciate just because they don't have the energy to eat that food. Do you think that may have been a potential impact factor? Your control data looked fairly good, but just curious. I mean, it may be a co-stressor.
Yeah, no, but both of those are great points. In terms of the metabolic activity, there is definitely a shift over development as they get older, they have greater metabolic activity. However, for diphenhydramine, it doesn't need to be metabolized to be toxic. I'd also conducted the mortality and behavioral analyses with diazinon, which is expected to be metabolized to be toxic, and we see a very similar trend. But for diphenhydramine, I don't know that is going to be a great descriptor, as doesn't need to be metabolized. But for other compounds, absolutely, that could be a driver for the difference in sensitivity. As in terms of feeding, that is also something to consider. Like you mentioned, I didn't have any issues with survival, so I don't know that for my studies played a role, but that is definitely, in terms of culturing, you do have to really overdose them with food to make sure that they survive. So they're definitely great points to keep in mind when evaluating this sort of thing. But at least for my work, I don't think either of those could describe the shift that I had seen. Mm-hmm.
You mentioned uptake through the gill.
Mm-hmm.
There's uptake through the skin, a lot of Toxicity and all that.
Yeah, I absolutely think there's uptake through the skin. In fact, a lot of, when you look at gill development, that's very negligible within those first couple of days. The surface area of the gill really doesn't start until a little bit after hatching, so mostly outside of what the FET guideline encompasses. And so the majority of the uptake over your embryonics in early larval stages will definitely be through the dermal surface.
Yeah, I have one more question. You mentioned behavioral endpoints in the very beginning of your presentation, and I was listening to a presentation a couple days ago from Baylor, and they looked at similar endpoints. And I was curious at that point, and you keep showing pictures of well plates. I was curious at that point, does volume, is that a factor into, I mean, because they can only swim so far.
Yep.
In a well plate, and I was curious your thoughts on that.
Yeah, there have actually been a few studies that have looked at the parameters if well size in relation to the length of your organism and the depth of the solution in your well, and a couple of other factors, just how are we influencing the behavior based on just our setup, not even the dosing. But that was all considered prior to doing any of this, and I had actually done a suite of naive behavior observations to even understand the influence of time of day and age on behavior before I ever conducted these studies. So to the best of my ability, I reduced those variables, but absolutely, if anyone's considering behavioral studies, all of that needs to be taken into consideration. Thank you.